slide and go to the next part of the design, which is applying this library of metastructures into making actual metasurfaces. When we were designing meta-atoms, we had to keep the unit cell small in order to keep the structure sub-diffraction, but there's actually a second method that we take into account that comes from the wavefront that we are designing. That is the Nyquist theorem. We're creating a certain phase profile. The Nyquist theorem tells us that, well, if we want to sample this, we need at least 2 samples per period. In a wavefront, period is marked by a change in phase from 0 to 360 degrees. So that tells us that in the time that our lens or deflector changes from 0 to 360 degrees, we need to have at least 2 unit cells. And from that, we can derive the condition on the unit cell, which in some cases turns out to be more strict than the sub-diffraction condition. The way to think about this, that in the case of a lens, making short focal distances, meaning strong curvature of the lens or the wavefront, is more difficult. In the case of beam steering, making large deflection angles is difficult. There's another aspect of sampling to consider, and that is that in reality, phase is continuous. If we want to sample this, we need to sample this well enough so that our wavefront aberration is not too large. You can see a little example of this here. This simulation represents a set of nominally equal of meta lenses, all, I should say, diffractive lenses in this case, with different number of phase approximation levels, but for the rest, all approximating the same wavefront shape. And you see here on the left, we have what would be known as a binary diffractive optical element, meaning that just have 2 levels of phase, 0 and 180 degrees. On the other extreme pointer, we have the purely or quasi-continuous phase. And if we look here at the maximum focusing efficiency we can get, you see that level approximation, even if all the structure is perfect, 100% transmitting, we can still only focus around 35% of the light. If we increase that, we approach the theoretical maximum, 87% of the light. In practice, you see that we need around 16 levels of phase control before the efficiency starts to saturate. So up to now, what I've shown about lenses could be done with a diffractive optical element. That's not why we're using metasurfaces at all. We want to use metasurfaces to do something that cannot be done with other types of technology. So let's take a look at this example here. So we're still making a lens with a slight difference that we are generating a different focal point for incidence and for TM incidence. The same equation focusing at 500 microns, but each of them is shifted 50 microns with respect to the origin. And for this, we're actually using the library a little bit before. We run this through the optimizer. You find here the GDS output of the software allows you to make the lens, and we see clearly reflected the fact that we are optimizing different phase. Then when we're not just content making the design, we also want to see how it performs after design is done and all the approximations have been made. And if we indeed simulate here for TE instance, you see that light is focused here in this yellow box. Then send in TM instance, light is focused over here, and only a small residual fraction of the stays with the box, and that gives us a combination of a beam splitter and a lens all in one. Ratio of rejection or one polarization to the other is around 2,000 to 1. If you go on the TotalLabs website and take a standard reported ratio, or variable numbers to what you find in classical components. You can take this idea further, not just managing polarization, but also, for instance, multiplexing over color. Here we made, not for a change, we didn't make a lens. Instead, we made a couple of holograms. We have this one image that we want to make for a red laser, this other image for a green laser. We can use the IFTA transform algorithm to generate the phase fronts for both, and use a library very similar to before, where we control both phase arms to have phase control over red and green light. Again, around 60,000 structures. We select from those, again, 16 by 6 structures very easily and generate just the same metasurface. So like this, we can control discrete polarizations, discrete wavelengths. In a lot of applications, that's not enough. In some cases, it is. And we actually do not want to control discrete wavelengths, but rather broader bands spectrum. And I'm sure many of you are aware that in this case, we need to do dispersion engineering, and we will make a different mapping all from the same set of basic calculations still, where we compare the phase at the central wavelength, but also the phase dispersion, the change in phase as we travel from one side of the spectral band to the other, while at the same time also controlling the transmission. So here you see a plot then of this process from the calculations using 6 types of structures, but just the other type. We see that we can cover the entire phase range. We have here a band of phase dispersion going from around 700 degrees down to around 500 degrees. At the same time, we can have phase change that we want, coverage. And this we can then apply to create a profile that's different, phase profile that's different for different wavelengths. There's 2 aspects to this. If for every phase we want to make a certain functional profile determined by the application what we want to do, the phase is only determined up to a constant. We can shift the phase up and down any direction we like, still have the same functionality. That gives us design freedom to have these different phase curves which depend on the wavelength and shift them with respect to each other, so that for every position in the lens, the phase dispersion that we still fits within the range of our structure. So functionality determines change in difference in phase that we need. By this design freedom, we can map that onto a phase change that we have available for structures. And this phase change that we have available is actually determined by the choice of our materials. So if we have higher refractive, we're going to have bigger delta phi range available. There's a very nice paper about this by Professor Multicolor that I recommend to everyone. And in fact, I recommend check this before you start designing. There's a couple of theoretical limits that you have to do. And the other aspect is the height of the structures that you can fabricate, which is in the end it's your aspect ratio, fabrication limit that you need. When we apply these principles to an example design here, we made an achromatic grating, which was designed to deflect light into a fixed angle range. If you take a standard placed grating like this, you would have a splitting angle from 500 to 650 nanometer here of around 1.5 degree. If we do it in the dispersion engineered way, we make a different component, flat component, but the angular spread is only 1/3 of that at around 0.4 degrees. So that's dispersion engineering. Let's now take that a little bit further into systems.